So there is our starting point. We're good. A little fuzzy on the green screen. We're here. We're Winter Hall. It's not too cold this morning. That's great. So live from Santa Barbara in Winter Hall, it is Westmont College Mayterm, CS-030. We are in the final week of classes. In fact, today is the second to last lecture we got. We've got one more lecture on Thursday, and then Friday's our final. Today's lecture is scheduled for 2 hours. We're communicating in real time on Slack, and I see that I've got a few people following on Slack today. Yes, the intro music is still playing because we're still introing, but no, that was a mistake. Thank you, Joy. It's good to have someone telling me what's up. We are scheduled for 2 hours today, and we're communicating in real time on Slack, and so I'm watching on broadcast questions more or less, although actually it's helpful to have people in the audience here channeling for me. So that's good. We are arriving, so let's just make sure that our gear is all set up. We've got notifications turned off as appropriately. My phone is off. I'm okay. I thought today actually I've sort of just wanted to read a particular scripture, sort of talked most of the things that I think I wanted to say during the course of the class about regulation and about the ways in which code has become a new medium for regulation. So not only is the law catching up with what code can and can't do, but code itself is taking the place of law in a little bit. I feel like we've kind of had a good conversation about that over the course of the semester. So today I'd just like to read a passage from Colossians to as we arrive and as we just are present and aware of what we're doing here, trying to fight against all those virtual and distractions that pull us out of being present with the activity in front of us, and oftentimes forgetting about the presence of Christ in our midst. So this is a selection from the book of Colossians in the New Testament. The translation is from the Message, and so I will just read it for us. It says, so, chosen by God for this new life of love, dress in the wardrobe God picked out for you: compassion, kindness, humility, quiet strength, and discipline. Be even-tempered, content with second place, quick to forgive an offense. Forgive as quickly and completely as the Master forgave you. And regardless of what else you put on, wear love. It's your basic all-purpose garment. Never be without it. Let the peace of Christ keep you in tune with each other, in step with each other. None of this going off and doing your own thing. And cultivate thankfulness. Let the word of Christ, the Message, have the run of the house. Give it plenty of room in your lives. I just felt like in reading this, it was just helped remind me what a different perspective the Bible and Jesus are asking us to take on what's going on in the world around us, because what I just read doesn't sound like anything I'm getting from media today, more broadly, social media or otherwise. And I think that in that conflict, there's some real wisdom to be found about how to react to what's going on in our public and political and social spheres. So this is a kind of a modern translation. It might be worthwhile to look at other more literal translations as well if you find it inspiring or helpful. Okay, for the class today, well, that's the class too. For the technical piece of the class, the administrative piece, we have a drone programming assignment due today. How is that going? Any comments from folks online or in class? Are you feeling okay about it? Any glitches? Any horrible glitches? Well, every time the drone lands, so the default way to tackle it, let's see. Let's see, I'm reading what James said. He says having glitches would require. Got it. Yeah. So do consider starting, James. The I think like the real basic thing that to do is to set your drone manifest to every destination so that any passenger is going to get on. That's the first thing, because that's just easy. Then you don't really have to think about where the passenger wants to go until they get on. And so then the passenger will get on. And then what you can do is you can just check to see if there's a passenger on board by checking drone.getPassengers, get one, or get zero, get destination. You can just kind of follow those method calls down the chain to see where that person wants to go, and then just route your drone there. And that's like the first thing that you should do in idling. And then otherwise the kind of the most optimal thing that you could do is you could look at all of the places that have people waiting for them, calculate the distance to all of them, find the closest one, and go to that destination. But I don't really expect people to do that in the short amount of time we have. And so if you can just find a place that has people waiting and go there and just have that be your strategy, you're probably going to do fine. So if you set that as your bar, find where people are, go there, and then just make sure that all the overhead associated with that supports that. So, making sure you're not going to the place where you currently are, making sure that you have someone on board, you drop them off before you go to a new place. That Great. And then if there isn't anyone, you can have different strategies. One is to go somewhere randomly. Another one would be to find a place that has someone waiting and go there. And that's easy enough, right? You just do a loop through the set of places, and you just check to see if there's someone waiting there. And as soon as you find a place that has someone waiting, you just go there and you exit your loop. You just return. You probably want to go through all the places. And if there's someone waiting there, by checking there should be a method, get waiting to embark. And then you just get the first person off that list, and you check to see what their destination is. Oh, no, sorry. If there's someone waiting at a destination, you just go there, period. Yeah, okay. So then that takes us to a quiz on chapter 17, which is due tomorrow, which is about tree structures. We're going to continue talking about trees today. I recommend spending some time on that quiz because a big portion of our final is about tree structures, and there's going to be some things that that you're just going to have read in the textbook, because we can't cover everything in the textbook, and a lot of the work in the textbook is pretty important for trees. So that's in our final on Friday. For the folks that are going to be in person and taking the exam in Winter Hall basement, Dr. Hunter is going to be here proctoring it for me, because I'm going to be giving a talk on another place on campus on Friday. So Dr. Hunter will be. What's that?
My parents will be there.
At that talk?
They're going to the conference. Yeah.
Oh, that's funny. Do they know that I'm?
Yeah, they were like, oh yeah, we're hearing your teacher talk like Friday at like 10. I was like, wait, that's our final.
How's that? Yeah, so Dr. Hunter's going to be proctoring. And then we'll be done. And then I'm going to be spending the weekend catching up on grading and working through the exam grades and the other things that haven't been graded yet. Okay, so last time, well, that kind of freaks me out. Do they watch online? Because they could.
No,
Okay.
Don't know anything.
All right, so last time we introduced the idea of data structures in the forms of trees. So we talked about the language of trees, so the vocabulary of trees. We talked about words like root and parent and leaf and sibling and child and descendant and ancestors, descendants and ancestors. And we talked about a path through our tree, and and we talked about subtrees. So that was sort of a vocabulary that we talked about with trees. We recognize that trees are a hierarchical data structure, and it's a kind of data structure that abstractly we run into all the time in places like file folders, and in any categorizations are often in tree structures. And the tree itself is very well aligned to work with recursive algorithms. And so it is often the case that when we want to do something with a tree, we have to write some kind of recursive algorithm to go through our tree and do the work. We're going to look at that in some depth today. Finally, we ended looking at a special subcase of trees called binary trees. So the difference between a tree and a binary tree is just how many children it has. And because of that, a binary tree is a subset of the trees that a tree with multiple children can have. The reason why we like that is because binary trees sort of distill the idea of a tree down to its minimal structure. And when you have a binary tree, you know there's only a left and right. You can do some specific kinds of algorithms centered around the fact that there's only a left and right in your tree. We looked at decision trees as being one of those kinds of a structure. So a decision tree is where each node has a question. And if you go left, it means that you're answering the question as yes. And if you go right, it means you're answering the question as no. And as a result, you can have a decision tree that, for example, answers 20 questions. And at the leaves of the trees are answers to the guess of what are you thinking about. You can also use them for more elaborate kinds of decision making. For example, in a medical domain, you might have a doctor that's essentially following a decision tree where each node in the tree is something about a symptom. Do you have a fever? Do you have a runny nose? Are you nauseous? And by following those answers, yes or no, down through a sequence of nodes, you get a rudimentary starting point from which you can do a more elaborate kind of diagnosis, which might involve getting tests about blood or other tests on your body. And then it might also involve doing other kinds of questions or surveys about medical history. In the technical environment, we looked at Huffman codes. And Huffman codes are this really interesting way of compressing data. And one thing that you can compress with it are characters. And we looked at the Hawaiian alphabet. We looked at how you could compress the Hawaiian alphabet with the Huffman code. And what the Huffman code does is it says we're going to represent each letter. If you're compressing the alphabet, we're going to represent each letter as a sequence of zeros and ones, but each letter is not going to have the same number of zeros and ones because they're not all going to be at the same depth in the tree. Some letters are going to be higher in the tree, and therefore it's going to take less zeros and ones to represent them. And so the way in which a Huffman tree encodes data or compresses data is by putting those characters which are most frequent towards the top of the tree. Lastly, we left talking about expression trees, and I think that's where we'll pick up on today. So a binary tree that is represented as an expression tree has operators, mathematical operators, at each interior node of the tree. And each leaf of the tree is a number. And by evaluating these expression trees, you're able, or by putting your expression into an expression tree, you're able to represent a mathematical expression that doesn't require parentheses, because the parentheses and the order of operations are represented by the depth of the tree. And so what I mean by that is if you look at the two expressions listed here on the slide, 6 plus 2 times 3, where 6 plus 2 is in parentheses, and 6 plus 2 times 3, we know that by order of operations, the first one's going to give you 6 plus 2 is 8 times 3 is 24, and the bottom one is going to give you 6 plus 6, which is 12. And so those two bullet points are going to be different kinds of, those are going to evaluate in different ways simply because of the presence of the parentheses. And so over on the right, we have two expression trees, and those two expression trees represent those two expressions on the left, but rather than doing it in linear math symbology, they do it in a tree format. So looking at those two trees, can you figure out which one maps to which expression? Let me ask someone online. Hey, people online, what do you think? Which tree maps to which expression? First one is the one on the left. That's our in-house consensus. I agree with you. And the basic way that you evaluate these trees is you have to go deep in order to solve the base problem before you can pop out. So if you look at the tree on the left, you have to go all the way down. You have to figure out 6 plus 2 before you can evaluate that subtree. Before you can figure out what you need to multiply times 3. Let me see if I can specify what I'm talking about. So before you can figure out what it is you want to multiply times 3, first you have to figure out what this subtree evaluates to. And this subtree is going to evaluate to 6 plus 2. That's going to wrap up and become 8. And so because you're doing 6 plus 2 first, you know that over here on this expression, well, that must be the first one. This is asking you to do 6 plus 2 first. The one on the right, this tree is expecting you to do 2 times 3 first. And so as a result, the 6 plus the evaluation of 2 times 3 is second. So that therefore must be this expression. Okay. So binary trees, one thing that you can do is you can represent expression trees with them. And like I mentioned last class, what we're talking about today is literally representing these expressions as data structures, whereas in previous examples, like when we looked at mutual recursion, we thought about expressions in a tree structure through talking about grammars, but we didn't actually ever represent an expression as a tree. We just used the fact that they work like trees in order to make function calls. But now we're talking about actually representing. All right, so we know about trees and we know about binary trees. The difference between them is how many children they have. So let me now introduce a new kind of tree. It's a special case of a binary tree, and the special case is called a balanced binary tree. Now, the thing that makes a balanced binary tree different than a binary tree is that it is characterized by the fact that each subtree, the left and right, have approximately the same number of nodes. So when we looked at the diagrams yesterday, we saw that in an extreme, you can represent a linked list with a binary tree structure just by only allowing the binary tree to use the left child. And if you only let a binary tree use the left child or the right child, it doesn't matter, you end up with something that looks exactly like a linked list because you're just not using the other link in order to represent your connections between nodes. So that's not good. That means that your tree is long and spindly. But a balanced binary tree is more bushy, meaning that each time there's an opportunity to take a branch, you fill out that branch before you follow down deep branches along the way. So visually, that might look like this. These are diagrams from our text. In this case, the one on the left, the red one, is more of a balanced binary tree, and the one on the right is unbalanced. And again, the definition of that is that the left and right subtree have approximately the same number of nodes. And the reason why we're being a little bit vague here is because depending on what kind of application you have, how close they have to be varies a little bit. But just as a general principle, the one on the left never has a subtree that is deeper or has a height that's more than 1 off of the right tree. Okay, that was sort of convoluted. So in the balanced tree on the left, no child's height differs from its sibling's height by more than 1. So if you look at the root node, the left tree has a height, including the node, as 1, 2, 3, 4, 5 is its deepest height. And over here on the deepest height is sort of a mixed metaphor. That's what you get for having trees that are upside down. And the right side is 1, 2, 3, 4, 5. So it's about the same. And then if you come down to one of these interior nodes, this node is balanced as well. So 1, 2, and then the right side is 1. So they're never off by more than 1. You may not be able to completely have a perfectly full binary tree because you just might not have enough data to fill out all the possible places where data can go. But this is a bushy tree. This one is not very balanced. And if you think about the root, the left side has a height of 1, 2, and the right side has a height of 1, 2, 3, 4, 5. So they differ by 3. And so that's not balanced really in any kind of application that I know. The fact that a balanced tree, the fact that a binary tree is balanced, the more balanced it is, the more you get certain kinds of efficiency. And when it's balanced, you can do some certain calculations to figure out how tall and how many nodes they have. So this calculation is an important one to understand. So if you would like to know how many nodes, say n, are in a balanced binary tree, that has a certain height, there's a formula that you can use to calculate that. So if you know that the height of your tree is 1, then the number of nodes in your tree is going to be 2 to the 1, or 2 minus 1. So if your height is 1, there's 1 node in the tree. That makes sense. That would be your root node. If the height of your tree is 2, then 2 to the 2 is 4, minus 1 is 3. So you have a tree with a height of 2 has 3 nodes in it. So that would be a tree, see if I can draw that. That would be a tree that looks something like this. That has 3 nodes in it. It has a height of 2. 2 to the 2 minus 1 is 3. So that's good. If we went one more and we said a height of 3, well then a height of 3 is going to look like this. 2 to the 3 is 8. 8 minus 1 is 7. Here's 1, 2, 3, 4, 5, 6, 7 nodes. So when we ask how many nodes does a balanced binary tree of height h have, we can use the formula 2 to the h minus 1, and that's going to tell you if your tree is perfectly balanced and it has that height, how many nodes does it have. So that would be a completely filled tree. So what I'd like you to do is we're just going to take a second and give you the opportunity to draw a completely filled tree of height 4 and count the nodes, and then just convince yourself that this formula is working correctly on a filled tree of height 4. So we will take maybe 3 minutes and do that. And if we can use the board here in the class. Just want to do it.
I was doing the technique this morning and I drew it out because there was a question about that.
Similar one. Okay, so we convinced ourselves that the math was right and that a tree of height 4 had 15 nodes in it. And we made this interesting observation that at each level of the tree has 2 to the h minus 1 nodes in it. So the first level of the tree has 1 node in it. The second level has 2. And the third level has 4. And the fourth level has 8. So that was sort of an interesting observation as well. Well, we have this formula. This formula says, given a height, how many nodes are in our tree? Well, we can also do the reverse formula and say, what is the height of a balanced binary tree if we have n nodes in it? And so we can just solve the formula for height instead of for n, and we can figure out that, well, if we have 15 nodes in our tree, that would be n equals 15, then 15 plus 1 is 16. Log base 2 of 16 is 4 because 2 to the 4 is 16, and the height is 4. So we can do the same thing with if our tree has 1 node in it, and n equals 1, then we have what is log base 2 of 2? That's going to be 1. So the height of a tree with 1 node in it is 1. So what we'll do is we'll take a second now and do the same thing that we just did, but let's do it the other way around. Let's draw 2 balanced binary trees with 7 nodes and 13 nodes and just check to make sure that the formula works. And then see if we can answer the question, what is the height of a tree that has 1 million nodes in it? And that's a little trickier, and we can talk about that when we come back. Let's take a second, draw a tree with 7 nodes and with 13 nodes, and try and identify what the height of those trees are. Okay, so we were just doing it on the board, and the answer to what does a balanced binary tree with 7 nodes, what's its height, that was pretty straightforward because it was a completely filled tree. A balanced binary tree with 7 nodes was exactly height of 3, and that matched the formula really well. But when we created the balanced binary tree with 13 nodes, we ran into a little bit of a glitch that was put there intentionally. And that's the fact that when you have 13 nodes, it doesn't give you a completely full binary tree. And so if you try and ask what is the log base 2 of 13 plus 1, or the log base 2 of 14, you don't get a clean number. You get a number between 3 and 4. What was it, 3.8? 3.807. And so what that number tells you is it tells you that it's going to take more than 3 levels. It's going to be a height greater than 3, and it's going to be, if the deepest path in your tree is the ceiling of that number, meaning you have to round up that number to find the deepest height in your tree. So that means that in a tree that has 13 nodes in it, 13 plus 1 is 14. Log base 2 of 14 gives you 3.8. That means you're going to have a tree of height 4 in order to capture all of your nodes. Although not all paths in the tree are going to be of length 4. So then that allows us to calculate what is the height of a tree with 1,000,000 nodes. Do you have the calculator available for that? Log base 2. The reason why, by the way, the reason why it's log base 2 is because there are 2 children. 19.931. So a tree with 1,000,000 nodes is going to need to be 20. It's going to have a maximum height of 20 because the log base 2 of 1,000,001 is 19.9, which means that most of the nodes are going to fit up to 19, but there's going to be overflow, and then you're going to have to put the rest in the 20th level. So whenever you calculate this formula, you need to figure out how high the tree is actually going to be, because you can't have fractional heights of a tree. You know that some paths are going to be ceiling of whatever h is. It works out easiest when it's a perfect power of 2. It doesn't often do that. Okay, so being able to determine how high a tree is going to be based on the number of nodes you have, and knowing how many nodes are going to be in a tree based on its height are 2 important formulas that you need to be able to work with. All right, so now let's go into our code and let's implement a binary tree. So previously we implemented a general tree, and so now I want to restrict this so that we're working with a binary tree. So let's cut over to Eclipse, and let me find my Eclipse. There we go. And I was working on some stuff earlier today, getting ready for class. And so we have a project here, which is part 2, and you can see that we have leftover from the previous class our other tree. So actually what I'm going to do is I'm going to cut out what's already here. So I was messing with it for class. And I'm going to take the source code from last class, which was our general tree structure. I'm going to copy it, and I'm going to put it in today's project. And then I will share it with whoever's online. I mean, I'm online. Okay. All right. So the first thing that we want to do is we're going to implement a binary tree. So what I'm going to do is I'm going to copy our tree, and I'm going to paste it. I'm going to give it a new name. So we're going to start with what we had before. We'll call it the binary tree. And trick you guys to read only for now. Then we'll open it up, and we'll start with our binary tree. And basically, things are going to be very similar. We're going to have this outer level tree class. It is going to be a generic class. So what we contain with the data that is in each node of our tree is not going to be dictated by the systems programmer. It's going to be left open for the applications programmer to decide at the time at which they want to use it what they're going to store in this class. So we previously had these methods create root and add a child and check the size. None of those things need to change because none of the things that are present in them, oh no, I take it back. We do need to fix add child because we're going to get rid of children in a second. But let's start at our node class. In our node class, we're still going to keep track of our reference to data, and that's going to be of type T, meaning what data we have is going to be dictated by the person who uses it. But instead of having a whole bunch of children, we're just going to have one node to the left and one node to the right. And when we initialize our class then, we don't know what left and right are going to be. We don't need data structures for it. So we're just going to say that left equals null and right equals null, which I think we would get for free anyway, but we'll just put it there to make it explicit. So let's go back now. That's what we want to keep track of in our binary node. Let's go back to our add child class. So when we want to add a child to our binary tree, it's not clear whether or not we want to add it to the left child or the right child. So what we'll do is we'll, I'm not sure how we want to do this exactly because we do want to be able to build up trees. So I guess what we'll do is we'll just change this class to say add left child. We'll be given a tree. And then we'll make another function called add right child. So we'll let the application programmer know about left and right children. I guess they know already because it's a binary tree. We'll just let them be able to do that. So they want to add a tree to the left side. So we'll say root.left will equal t.root. So we'll unwrap the node structure that's present in t, our parameter, and we will attach it to our node structure that's on the left side. If there is something already on the left side of our tree, this is going to replace it. So this is possibly a destructive act because it's changing what the left side is. So instead of saying add left child, I'm going to change the name of our method to set left child so that it's more clear that we are possibly going to be changing it. And then we'll make it set right child as well. We'll spell right the traditional way. And then we will say root.right equals t.root. Right, that fixes our highest level implementation. Now within our node, we're going to need to do something about our size class. Our size class is a recursive class, and the way that we were doing it before is we were saying, okay, well, the size of our tree is going to be equal to 1 plus the size of our children. Well, we can still do that. We're just not going to do it with the fast enumeration. We'll just say that our size is going to be 1, and then we're going to add to that the size of our left node. That'll take care of the size of our left tree, and then we'll also add the size of our right tree. And we'll return what the result is. That seems pretty good. Now, of course, it's never any good if you don't actually test it. Let's take our tree test, and let's copy that, and let's paste it as a binary tree test. Our binary tree test isn't going to compile when we actually build it with binary trees because we're using our add child method, but we'll go through and we'll edit that out. So we'll start by just checking whether our constructor works okay. And that if that doesn't fail, then we know that that passed. And so we don't actually end up using that variable, so we can just call the constructor and never use the object that's returned. In our second test, we will create our binary tree filled with strings. And we will create the root Elizabeth, and we will check to make sure its size is 1, so that's a straightforward test. And then in our third test, we will go through and let me go through and just make sure that it uses binary trees. All right, so in our third test, we're creating a root, which is Charles, checking that the size is 1, creating a root that's William and making sure that the size is 1, creating a root that's Harry. And now we have 3 nodes, and instead of adding children, we're going to add William to the left node and Harry to the right node. And let's see if that compiles. Okay, again, we need to spell it the traditional way. And we said that the new name is set left child. set right. Okay. Great. We'll create a new tree, T5, that's rooted in Anne, and T6 that's rooted in Andrew, and T7 that's rooted in Elizabeth. And we'll say that we want to put T1. Now this is a little bit of it. We have to decide what we want to do here, because previously when we were creating the overall root, T7 has 3 children, and we can't do that in a binary tree. So how should we handle that? You want to just make another interior node? Okay. So let's make T8, and we don't really have an actual person that belongs there. So we'll okay, so that means that T7 can have 2 children, and let's see, T8 can have 2 children. So we'll say T8 that child is going to be set left child. We'll set T8's left child to be T1, and we will set T8's right child to be T5, and then we'll say T7's set left child to be equal to T8, and we'll set the right child to be equal to T6. Now we just have to remember that we added another node there, because when we do our tests, we have to make sure that we get the right number. So I think we should have 7. Can't type. All right, so if we run our binary tree test with coverage, not all the tests pass. Okay, so what do we do wrong? We said that we wanted to calculate size, and we got some sort of a problem. Oh, we got a problem because sometimes the left and right node are null. So we can't always assume that the left and right node have children there. They could be null when we get to the bottom of the tree. Previously, we didn't have to do that check because our fast enumerator just wouldn't give us any data. So we'll just say if left is not equal to null, then we'll add that to our aggregate. And if right is not equal to null, then we'll add that to our aggregate. So once again, testing has saved us. So if we hadn't done that beforehand, we would have gotten, if we had tried to distribute that code without having tested, we would have had bugs in it. So now test T2 passes, and test T3 is failing, probably a similar situation. Let's see, so we have a problem that we get a null pointer exception if we say root.left. Oh, because I suppose if we haven't set a root, then root is going to be null. So there's not going to be a left if root is null. So why is that happening? Let's see. We go to our test, we're saying that T8, oh, that's because right here, I didn't change, when I cut and pasted the code, I didn't change these 2 lines to T8. So in this case, what our test did is just tested to make sure that the test was okay, and it wasn't. So and nonetheless, it showed me that there was an error in my test case. Now if I run it again, now we're passing everything. So we want to look to make sure everything got covered. We can see that all of our binary search tree code, our binary tree code got colored green. That's pretty good. Okay, so that's an implementation of our binary tree. Any questions about that? That was kind of straightforward. Anyone online? Okay, so let me just ask you something. When we calculated the size of our tree, what we did is we said that the size of our tree is 1 plus the size of the left and the size of the right. What would we do if we wanted to calculate the height of our tree? How would we do that recursively? We obviously don't want to add it. The height of our tree isn't the height of the left and the right. Well, if you think about it recursively, and you know you're sitting at the root of a tree, and let's say that you knew the left side of your tree, starting at the left node, had a height of 10, and the right side had a height of 1. What would the overall height of your tree be? Left side's 10, right side's 1, and you're which one of those? Because the height is the highest, right? Right, plus the 10. So what did we do? We said it was 1 plus the 10. So what's the general algorithm for figuring out the height of a tree recursively? And we had 2 choices. We had a 10 and a 1. So how did we decide which one we wanted to use for the height? But 1's all the descendants from the right, right? So what was it about the 10 that made us want to choose that? Because it's longer, right? That's right. And so the height of our tree is the longest. So if we think about doing that recursively, the general pattern is going to be the height of our tree is going to be 1 because of the node we're at, plus the longest of our 2 children. So rather than adding everything, let's change our height. Let's create a new method called height and add this to our node. We know that the height is going to be I never remember how to spell height. I get the E's in it. I want to spell E's. Let's assume that I'm spelling it right there. We still need to know what the height of the left side is. So we'll say the integer left height equals left.height. So there's a recursive call for us. And we're going to need to know what the right side is. That's going to be the height of the right. But what we're going to return is not going to be the sum of all those things. We're going to say if left height is greater than right height, then what do we return? What do we return? Left height plus 1. Great. In fact, since we're just adding 1, we don't actually even need a variable to hold the aggregate. Otherwise, we'll return the right height. So actually what's happening here is that we're returning 1 plus the highest, 1 plus the deepest tree, but if both of them are equal, it doesn't matter, but we end up doing 1 plus the right side. Why am I getting glitched? Because I'm never using it. Okay, so now this is internal within the node, so we need to create access for the people who want to use it. So we'll do this. We'll say the height of our tree is, you know what? We need to also check to make sure this isn't null. We have to say if root equals null, then return 0. Otherwise, we'll return the size of the root. Our testing didn't catch that case. We never tested the size of an empty tree, so we'll add a test for that. And likewise, we'll do the same thing here with height. If the root is null, then it's 0. Otherwise, we're going to return root.height. Okay, so let's make our tests reflect that. Let's go back and make sure that we get the right answer here. And we'll go ahead and add our size check in this first test. We'll say binary tree string t equals this new string, and we'll make sure that assert true that t.size equals 0, and assert true that t.height equals 0. And if we run just that first test, do coverage of just that first test, we can see that we're testing one condition with our height, and it looks like we're testing multiple conditions with our root. Why are we testing multiple conditions here? We shouldn't be testing root.size. Why does that happen? When we create our binary tree. Okay, so let me explain what I'm having a problem with here. We ran one test, And that test, oh no, we ended up running lots of tests. Okay, that's what. Let's just try and run one. Just run this test, please. There we go. So we just ran the first test, and as I look at the code coverage, now I feel better. It shows that line 62 and line 71 were both run, but 65 and 74 were not run. That's because we never called size and height in a tree that had any data in it. That was our test. So in our test, we're going to go back now, and now we're going to test the same kind of thing, but now we'll test on a tree that has size 1. And so when a tree has size 1, it better also have a height of 1. And so now if we run the second test, we look at the coverage. Oh, it didn't pass. Why did it not pass? Well, the first thing to do is to make sure that your test passed. Our height test didn't pass. So what happened? Oh, again, we didn't check whether or not we had null. Okay, so I'm going into the node class. I'm going to make sure that we don't try and follow the left-hand path if left is null. So we'll assume that the height is 0, and if left is not equal to null, then we'll find out, we'll say the left height equals the height of the left side. And we'll initialize the right height to be equal to 0. And we'll say if the right is not equal to null, then we'll reset the right height to be equal to. Okay, test saved us again. That's why I'm a fan of tests. Try that again. We'll run the second test coverage. And it passed. And if we look at the coverage, now you can see that in our height of our tree, you can see that we're only testing the height of a tree that has some nodes in it because we're only running the second. All right, now let's check the height of our last tree. And so let's see if we can make sure that we get this right. We know that T1 is going to end up having a height of 2. And we know that when we put T1 onto 8, that gives us a height of 3. And then when we put T8 on 7, that gives us a height of 4. So we are expecting that the height of T7 is going to be equal to 4. And I can't spell height. Now what I'm going to do is I'll just run all of our tests, and we can get confidence in all of those tests. Passes good. When we look at the coverage of our code, we can see that every branch of every function has been tested, so we have high confidence that what is happening here is working. Although you can see that because we never wrote a test for when the tree was 0, we weren't able to catch that bug. So you can only catch bugs for the things that you end up writing tests for. All right, so what did we just do there? We just implemented the binary tree. And in order to implement the binary tree, the primary thing that we did is we changed our node definition so that instead of having an array list of children, it just had a left child and a right child. That was the primary thing we did. In order to make that work, we had to go back and we had to change the code that called those nodes as well. In order to demonstrate the way that these recursive algorithms work, I also added a height method to our code so that we could see the way in which a recursive algorithm can be used in different ways. So in size, what we did is we said our size of our tree is 1 plus the size of our left side plus the size of our right side, because the size of the tree is all of the nodes. But when we wanted to calculate the height of our tree, we said, well, it's going to be 1 for the node we're currently at plus the longest of the two subchildren. So we had to do an if statement to determine which one was the longest. We had to do a little careful management of the null pointers as well. All right, so now let's talk about another way of thinking about recursion through our tree. And I want to talk about traversing through a tree. And there are 3 different recursive styles that we can use to traverse through a tree. We can do pre-order traversal, in-order traversal, and post-order traversal. When I talk about traversing a tree, what you should bring to mind is the way that we iterate through a collection or iterate through a linked list. If you remember our iterator for our linked list or for our array list, it was something that walked through the list one at a time and visited each one of the nodes. Well, traversing a tree does the same thing as well. It goes through our tree and it visits each node in our tree in a particular way. But there are different ways that we can do it. And those three ways generally fall into the pattern of pre-order, in-order, and post-order. They are recursive algorithms, and I would like to walk through them. But we're about halfway through the class, and I think we should just take a 2 or 3 minute stretch break. And then when we come back, we'll start talking about these three different ways of traversing a tree. And then we'll look at implementing them in the code. Okay? All right. So let's see. While you're gone, think about pre-order. Oh gosh, I don't think I had the overhead slides. So while we're on break here, I realized that I wasn't showing you my slides along the way, or I wasn't showing you the screen along the way. So let me show you the binary code that I wrote. I'll just leave it up on the screen for now because that wasn't being generated. Okay, so we are talking about traversing a tree, and we said there are three different styles of doing that: pre-order, in-order, and post-order. While we were on break, I realized I didn't have the screen live when we were coding, so I will put that code on Canvas for you so you can take a look at it in time. So traversing a tree. So pre-order means that recursively you're going to do this pattern. First, you're going to visit the root, and so if we consider the nodes on the slides right there, the first one you're going to visit is the red one, and then you're going to recursively visit each child, and you're going to complete the recursion before you go on to the next one. So first you'll visit the red one, then you'll recurse on the green one, and then you'll recurse on the blue one. If you have a binary tree, that means you do root, left, and right. The important thing is the word pre And pre-order refers to the fact that you do your root tree first. If you had an n-ary tree, or a tree that had multiple children, you would visit the root first, and then you would visit each of your children in order before being done with this subnode. Pre-order, the root comes first. Let me jump to the last one, post-order. Post-order, the root comes last. So when you recursively traverse through a tree using a post-order pattern, first you visit the left side in a binary tree, then you visit the right side, and then you visit the root on the way out. For an n-ary tree, you go through each of the children in order, and then you visit the root on the way out, or as you're returning from the function. So post refers to the fact that you're visiting the root node last. So the final way that you can traverse a tree is in order. Now, in order only really makes sense for binary trees because it places the root between the left side and the right side. Pre-order, the root comes first. Post-order, the root comes last. In order, the root comes in the middle. And so when you traverse a tree using in-order traversal, you go left, root, and then right. Oh, my slides are wrong here. And they're wrong enough that I'm going to fix them before the world sees them wrong, before you learn the wrong thing. So behind the scenes here, whoop. What is wrong about this is I've color-coded my stars wrong. So the root is red, and the right. So let's try again. So in order means that you do left side green, root red, right side blue, and you do it in that order. So 3 options: pre-order, in order, post-order. The difference for a binary tree is when you visit the root. So let's consider what that means. If we are going to traverse a tree starting at the red node and not going up into any parent pair, and if each time we visit a node, what are we going to get for the sequence of letters that we see in a pre-order traversal? And let me do this one for us, and then I'll give you a chance to do one of the other ones in a second. Okay, so pre-order traversal means that you visit the root first before you visit each of the children in turn. So pre-order means then that you'll see the D first, then you'll see the left side, H, and then you'll see the right side, I. Good. In order means that you'll do left side, root, right side. So you'll get H, which is the left side, D, which is the root, and then I, which is the right side. Post order means you'll do the root last. So you'll visit H first, then you visit I, and then you visit D. So 3 different traversals. They've traversed all of the nodes of the tree, but they've done it in different orders. Let's take a look at another one. What do you get if you do those 3 traversals starting at the G? Want to give a shot? G, great. Okay, usually at this level, everyone kind of gets it. It's pretty straightforward. You've got 3 nodes, 3 orders. It kind of just comes down to where the root is. You look at it, pre-order, there's the root. In order, there's the root. Post-order, there's the root. And otherwise, the N and the O maintain the same relationship. Gets a little bit more complicated if we start up at a higher level. Because now when we do our recursion, we have to walk through and ask the same question at each one of our children's nodes. So let me walk through this one with you, and then I'll give you a chance to do the different node. So if we do pre-order traversal, it means we're going to visit our root node first and then our children. So first we're going to see B. That's okay. Now we're going to do left side, right side, but before we're finished with the left side, we have to completely finish out the left side, left branch of our tree, so we have to recurse. So the next thing that we do is we go down to our left node and wait for a second. We say, okay, now we're at our left node and we're doing pre-order traversal here. Okay, pre-order traversal means we do D. Then we do left side. So we go down to our left side. Pre-order traversal means we do H. We're done with this node, so we come back up. Now we've already done D and H, so we do I. We get down to, we visit I. Now we're done with this entire branch. We come back up, having already done B, we now do E, visit the right side. We're doing pre-order, so we see E, and then we see J, and then we see K. So that pre-order pattern is being maintained at every single sub-branch of the tree. If we do in-order traversal, we're first going to do the left side before we do the right side. Let's say I can't get rid of the red without doing the whole thing, so I'm just going to erase everything. So in-order traversal means that we first do left, then we do node, and then we do right. We do it completely recursively. So we start at B, we put a little token there, and we say, okay, first we're going to go left. Now we're at D. All right, we don't immediately write D just because we went left. We're doing in order. So we go left again at D, and we say, okay, the first thing we type in order then is going to be H. Now we're done with H, and we return to where we were, D. Well, we're doing in-order traversal at D. We've already done the left side, so now we do D. And now we do the right side, I. We're now done with the whole left branch. We come back up to the B level, and we're doing in order, so we do B. Now we do our right side. We don't immediately write E because we're doing in-order traversal. Before we write E, we go ahead and take care of the left side, which is going to be J. Then we come back to E. Then we come back to K. Then we return to B. We're already done with B, and we've completed our subtree. So the answer ends up being H, D, I, B, J, E, K. By that? All right, so let's try the last one, which is post-order traversal of the tree. And so if we do post-order traversal of the tree, that means we do left side, right side, and then the root. So we're starting at B, but just because we have a reference to B doesn't mean we're handling it first. Next, we have to go down to D. We have a reference to D, but we're not handling E yet. We first have to go down to H. H has no children, so we don't have any children to process first, so we go ahead and do H as the first thing we visit. Now we come back up to D, but we don't do D because we're doing post-order. Before we can handle D, we have to do the right side. So we go to the right side, which is I. There's no children, so we write I. Now we come back to D. Having already handled the left side and the right side, now we handle D. Continue back up to B. We don't handle B yet. First we handle the right side, so we have a token at E. We don't handle E yet. First we do the left side, which is going to be J. Now we come back to E, but we're doing post-order, so before we can handle E, we've got to finish the right side, which is K. Now we come back up to E. Having handled J and K, we handle E. Then we go back up to B. Having handled left and right D and E, now we do B. Okay? So one thing to notice here is that when you do pre-order traversal, whatever root you start at came first. And when you do post-order traversal, whatever root you started with came last. In order, it depends on how many children there are. You can't say for sure it's going to be in the middle. It depends if it's a balanced tree or not. Okay. So let's try from the very root. You want to see if you can come up with it? Okay. So pre-order. A, good. We've done A. Well, you're doing so think about it as references. So you did A, now you're at B, and imagine you're starting at B and you want to do pre-order traversal. So now what happens? In pre-order, you handle your root first. Right. E, D, but you can't finish the D node until you've gotten the subset. There you go. H. Then you handle I. Good. Now you go down the right branch. E, J, K. Good. Now you're back up to A, and now you're doing the right branch. Good. Good. So we did here, 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 here. Okay. You know what's coming next. I don't know a way to. I need to get better at my slide management. Okay, let's try now doing in order. This is a little trickier. So you know we're starting here, but we can't handle that one yet. We have to handle it. Right, so let's put a marker on A. Which way do we go first? Okay, so let's put a marker on B. If we're starting at B, which way would we go first? Okay, marker on D, which way do we go? Okay, is there anywhere else to go? H, D, I, good. Oh, sorry, I'm writing it in the wrong spot. H, D, I, good. Now you're back up on B. You've handled the left side. But you do B first because you do left, root right. B, then marker here. Imagine you're starting at E. You're doing in order. So what do you do first? J, E, K. There you go. Now we're at A. Then we do A, right? Imagine you're starting at C. Now imagine you're starting at F. Now you're back at C, having done your left side. And G, great. All right, so the pattern that we visited for in order is we did here, 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 here. Last one is post order. Erase, 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 erase. Okay, post order. Marker there. Marker there. Marker there. Okay. Now you're at B, having just done the left side in your post order. So put a marker on E and say, okay, and I'm at E. If I started at E, what would be next? There you go. Okay, now you're back at B. You've handled the left and right side. B, good. Okay, now you're at A. You've handled the left side. Not yet, good. So you go to C. Okay, you're at F. Now what do you do? L, M, F. Okay, you're at C, having handled the left side. N, O, G, good. N, O, G, C, A. All right, so the pattern with post order was dum, 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 here, 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 boom, 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 doom, 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 doom. So subtle. Important difference the important thing to realize is that each one of these techniques is going to visit every node, but they're going to visit each node in a different order. And one thing you saw me doing is I was differentiating in my mind about where your reference was as opposed to where you were processing. So your reference goes to a place before you think about processing. So you start with your reference at the top, but you don't necessarily process that first. Okay, so let's implement those in the binary tree. And what we'll do is we'll say, we'll just have it print out for the time being what the values are in those trees. So cutting back to Eclipse, how are we still connected? Do we need to connect? Okay. Good. Okay. All right. So what we want to do is we want to implement in our binary tree these different ways of doing a traversal. So let's just shrink these down so that we can see a little bit. And what we're going to do is we're going to add a new method, which is going to just print stuff out, and we'll say print in order. And so what we're going to do when we print in order is we're going to, if our root is not equal to null, got to make sure that, true. Then we want to say, tell our root to print in order. So that's calling recursively on our root, on our node class. So now we need to implement a print in order in our node class. So let's clean that up so we can see what's going on here. So we will print in order. So what that means is that we handle our current node before we go down to each of our children. So we're printing. So what we're going to do is we're going to say system.out.println data. So we're going to print out the data that's associated with our node. So that's first. Now we're going to handle the left and the right. So if left is not equal to null, then we are going to call left.print in order. That handles us, that handles left, and now we're going to handle the right side. So if the right side is not handled, then we'll print in order. That's it. Handle ourselves, handle the left, handle the right. Well, you might not find it. Oh, sorry, that's not in order. That's pre-order. Oh. Wow, that was confusing. Well, as long as we're on a roll here, let's go ahead and do the other one. As long as we're on a roll in which I'm making big mistakes. Okay, we know we have pre-order. We also know we have in order. We have post order. We need to implement them in our nodes. Let's see, our recursive call is going to print pre-order also. Okay, when we said when we handle in order, then what we do is we handle our left side first. Then we handle ourselves. Then we handle our right side. So that's doing an in-order traversal. For our post-order traversal, we first handle our left side. Then we handle our right side. Then we handle ourselves. So I find this kind of elegant. I think it's really interesting how the difference between these traversals just have to do with this recursive call. Left, center, right, left, right, center, center, left, right. Now it'd be nice, we want to make sure that this is working as well. So let's go make sure that our tree looks like what we want to make a test for ourselves. I don't want to use one of these because it's a little bit elaborate. Let's just get a very simple tree here. Grab this. We'll make a new test for ourselves. All right, so in this test, we are having a node T1, we have T2, and we have T3, and T2 and T3 are the children of T1. So we have Charles on the top, William on the left, and Harry on the bottom, on the right. And we're not testing size in this test, so we're not going to worry about that. Instead, what we want to do is we want to just call, for the time being, T1.print in order. This doesn't return anything, this just outputs to the console. So we're not going to be able to really test anything about this because we would have to have some sort of thing that we're returning. Well, actually, let's test with pre-order, but why is this not? Fine. Save everything. There we go. So what do we expect to see? We expect to see that this test is going to output to the console Charles, William, Harry. Let's see if it does that. Looks good. So we'll put all these in one test. All right, we'll just put in here what we expect. For pre-order, we expected CWH. For in order, we expect WCH. For post order, we expect WHC. Make sure we call the right method. On that. Pre-order CWH, Charles William Harry. In order WCH, good. Post order WHC, pretty good. Okay. Thoughts? Thinking through it. Okay. I want to expand on this idea, and I want to introduce something called the visitor pattern. The visitor pattern is a way of abstracting what we just did with our in-order, post-order, and pre-order so that we allow the systems programmer to control the order in which the nodes are visited. So that was the pre-order, in-order, post-order. So that's going to be provided by the class. But what happens at each node is going to be based on what the application programmer wants to do. So it's all well and good that we can walk through these nodes in a particular order, but someone who's using our class is going to want to do something as you're walking through the tree in that order. And it's very difficult to give a user of our tree class the ability to work in our data structure and still keep the encapsulation and the implementation abstract from them. And so the visitor pattern is a way for allowing them to do work at each one of the nodes through these different traversal patterns without revealing to them how we're implementing the tree. So the way we're going to do this, think, for example, in the example we just had where we printed out each node of the tree, you can think about the printing out of each node of the tree as something that the application programmer cares about. As someone that's implementing the tree, you don't know that printing out the tree is anything helpful. Printing out the contents of the tree doesn't seem like it's necessarily what you want to do. You might want to have a user that wants to print out the contents of the tree, but you might want to have a user that does something else with the contents of the tree. And so what we're going to do is we're going to put that printing out function into its own class. And we're going to make that separate class be the thing that does the visiting. So you can imagine that we're going to make this object, and we're going to send that object on a walk through our tree. The object is going to walk through the tree in one of those three patterns. And each time it gets to one of those nodes, we're going to tell the visitor, that's the thing that's walking through the tree, we're going to tell the visitor that it's at one of these nodes and give it the opportunity to do something with the data that's at that node. So the visitor pattern is like an iterator that goes through the tree, and the visitor is going to get to see the data, but it's not going to get to see any of the implementation. The way we're going to enforce this is we are going to give the user, we're going to create an interface within our class that people who want to write a visitor can implement. And that's going to be defined by the systems programmer. And then the application programmer has to write the visitor that actually does something. So what we will do in this case is we'll write a visitor that's going to calculate the size of our tree. And that we're going to do that by having, as our visitor walks around the tree, we'll have the visitor count up the nodes. All right, so let's implement that visitor pattern. This is going to be a little bit mind-bending if it's the first time you've seen this. So here we go. First of all, the place we're doing this is in our binary tree, because otherwise these orders don't really matter much. Or at least in order doesn't make sense. The other ones can. And what we're going to need to do is we're going to need to now define an interface within our class that is what we expect the visitors to be like. We need the visitors to have some properties that we can depend on so that we can actually make them work on the behalf of the applications program. So I'm going to create a new public interface called a visitor, and what it is going to visit are objects of type T. That means that it's going to get delivered something of type T in order to handle that, because T is the type that's in each one of the nodes. And what the visitor class has to do is it has to implement something called handle. And it's going to be given something of type T each time it gets called. Now you can see that what I've just defined there is a function header. I haven't implemented it. That's because this is an interface. It only says that if you make a class that conforms to this interface, you have to write the handle class. But you can have it do whatever you want. All right, but now we assume that we have something called a visitor class that's going to handle the nodes as they go through. Let's go down here and let's transform our print and our print pre-order, our print in order, and our print post order. And what we're going to do is we're going to call it instead, we're going to call it visit in pre-order. And we're going to kick it off and say node visit pre-order. And what we're going to take is we're going to take one of these visitors, type T, with us as we visit. And I got to spell it right. So we're going to take one of these with us as we travel through the tree. Send it through the tree like that. We have to rewrite this before it's going to work. All right, so that's going to be what happens if we do in order. We're going to do the same pattern for pre-order. We're going to do the same thing for in order. We're going to visit each one of the nodes in order, and we're going to take a little visitor along with us. And then in post order, we're going to visit in post order, and we're going to take the visitor along with us. All right, that is calling the node version of it. So let's come up here and change our node. All right, so previously we had print in order. In this case, instead, we're going to visit in pre-order, and we're going to take the visitor that's traveling along with us, expects to handle things of type T. The work that we did before is we printed out the data. We don't want to print out the data necessarily. We want to do whatever the user of our class wanted to do. So we're just going to say v.handle the data instead. And if the user wants to print out the data, well, in their handle class, and they can implement print. But they don't have to implement print. They can do whatever they want. So they can handle it however they want. And then we're just going to continue the pattern. We're going to say, go ahead and visit pre-order down the right side, and we'll send the visitor along. And we will visit pre-order down the right side, and we'll send the visitor along. Main thing being here that we haven't dictated what the user is going to do with the data. Well, same thing with in order. We're not going to print out the data. We're just going to say do whatever the visitor wants to do with it. And then we just need to clean up the rest of this so that it compiles okay. Visit in order, welcome our visitor. Left side visit in order, send the visitor. And right side in order, send the visitor. Lastly, do the same work with post order. going to print out. We're going to do whatever the user wants to do. And all right, we're compiling okay. We're doing our visits and everything looks fine. We just haven't used it yet. So let's show how we can go about using this. Our tree no longer compiles because we got rid of our prints and we expected prints to work there. Well, let's see. In order for this to work then, we're going to have to declare something that is going to work like our visitor class. So let's make a little class which is going to be a visitor class. We'll say our visitor, and it is going to implement the binary tree string class, or binary tree dot visitor on a string. Public. And what does something that implements the visitor class have to do? It has to have a handle method. So each time our visitor goes through this tree, it's going to be, this method is going to be called, and what do we want to do? Well, we can print out the data that we visited. And so actually, let's call this our printing visitor. In our test now, before we send our visitor on the trip, we need to make one. So we'll say new our printing visitor. And great. Now we're not going to visit print an order, we're going to visit pre-order. And we're going to send our visitor along. And each time it visits a node, it's going to print out the data. Then we're going to do in order, and the visitor will do the work of printing out. And then we'll do post order, and the visitor is going to do the work of printing out. Now if we run our test, everything passes, and in addition to that, you can see that we're getting the right ordering. CWH, Charles William Harry, WCH, William Charles Harry, WHC, William Harry Charles. So what we did is we abstracted this idea of the work that we're going to do each step along the way, and instead created this class which has a particular method in it that gets called. I want to do one more with this visitor pattern, which is to I'll show you how the visitor pattern can count the size of our tree. To do that, we're going to need a different kind of visitor. We'll say this is going to be our size visitor. And each time it goes to a particular node, we're just going to completely ignore the data. We don't even care what the data is. We're just going to keep track of it. And we're going to have an instance variable here, which is our aggregate variable. And it will start with 0. And each time we visit a node, we're just going to add one aggregate, make this public so we can get to it. Because this visitor is going to move along, and because that instance variable travels with the visitor, as we visit node to node to node, our aggregate integer is going to get increased as we go through. And it doesn't matter which order we go in because we're going to visit all the nodes, so we should get the same thing each time. And if we come down here, and in addition to saying our printing visitor, well, actually, let me copy this so we don't. After, when we start, we know that v.aggregate, the variable inside it, that is keeping track of how many places it's visited, that's going to start as 0. But after we visit things in order, based on the nature of our tree, that better end up being 3. Because after visiting pre-order, it will have 3 elements. we can then we will reinitialize our variable equal to 0, and we will make sure that it is equal to 0, and then we'll visit our tree again and make sure that it gets updated to 3. Set them equal to 0. We'll visit our tree, make sure that it's equal to 3. Pass, but I'm not convinced that it ran the code. Great. So now we use the visitor class in a very different way. We use the visitor not to print something out, but to keep track within itself of how many nodes it visited. Great. That's the visitor pattern. The visitor pattern doesn't have to be used in trees. The visitor pattern can be used in a linked list. You can imagine writing a visitor that gets passed down a linked list and does something very similar. Visitor pattern can be used in all different kinds of contexts along the way. All right, so the last kind of tree I want to introduce to you today is called a binary search tree. The binary search tree is a tree. The binary search tree is a binary tree. The binary search tree is a binary tree that has a special pattern in the data that it contains. And that pattern is that the descendants to the left have smaller data values than the node data value. And the descendants to the right have larger data values. So there's a left and right, and there's kind of a similarity here between our in-order traversal pattern. If you imagine that everything to the left has a lower value than the root, and everything to the right has a higher value than the root, then you've got a binary search tree. Looks something like this. Pardon my janky graphics. What this means is that you have some value of a variable x at a particular node, and what you know for sure is that everything to the left-hand side, every value that's in any node, any descendant to the left-hand side, is all going to be less than x. And every node that is a descendant from the right-hand side, regardless of the shape of the right-hand side, all of those nodes are going to be greater than x. So you've got a left-hand side and a right-hand side. So what you could do then is you can draw some binary search trees to make sure that you understand them clearly. Now the thing about a binary search tree is the way in which you draw it depends on the order in which elements are inserted. And so I want to demonstrate that by drawing one of them with you. And in order to do that, we actually need some data to enter in. And so I don't want to bias this, but let's see. Lisa, can you pick 4 letters from the English alphabet in some random order?
Well, how about my name?
Hey, what a great idea. I actually hadn't thought of that before I said it, but we'll go with it. All right, so what we're going to do is we're going to draw a binary search tree, and we're going to build it out as we enter the letters. Okay? The first letter in your name is L. I don't have a lot of space in this slide. So we would have one node that has an L. Wow, look at that L. It's like precise. Perfect. Next letter is I. Does I come alphabetically before or after L? Before. I know. It's just your name. Given what we know about binary search trees and what we know about lexicographic ordering, should I go to the left branch or the right branch as a result? The left. So this isn't really a good match for spelling your name, but it's a good match for keeping track of it. So now we have something that is still a binary search tree. It has a height of 2, it has a size of 2, it has 2 nodes in it. Now let's add S. Where does S go? All right, now let's add A. Where does A go? It goes before L, so we know it's got to be on the left side. Now we go down to A. Is it before or after A? All right, sorry, before or after I? Before. So if we create a binary search tree by entering the letters of your name in order, we end up having L, I, A, S, like that. This is a binary search tree because at every moment in this tree, the letters to the left are less than the elements to the right. But the order in which you insert them makes a difference. So let me just see if I can recreate that somewhere here where we can kind of look at it. I can't draw very well. L-I-A-S. That's just a reminder. All right, so let's try doing the letters of your name in reverse order. So in that case, we're going to start by dropping the A at the root. Now we want to add the S. Where does the S go? Right. Now we start getting a little tricky. We want to add an I. So starting at the root, should the I be on the left or the right? Right. Now we go down to S. Should the I be on the right or the left? Now we want to add L. Should it be on the right or the left of A? Or at the S, should the L be on the right or the left of S? The left. H-I-J-K-L. Right. So a very different shaped tree. This one here had 3 elements down the right. This one here has all the elements down the, sorry, the purple one has all the elements. Purple one has 3 elements down the left side, including the A, including the L. The one on the right has all the elements going to the right of the root. Both of them are binary search trees because they both obey the property that every single node in the tree only has elements to the left that are less than the root node and right elements that are greater than the root node. So what we see from this is that a binary search tree is not unique. You can have multiple binary search trees from the same letters that you're keeping track of, or whatever it is you're keeping track of. Of course, you could keep track of numbers. You could keep track of things that can be alphabetized. And what that means, that generally speaking, is for a binary search tree, all the elements have to be comparable, meaning that there's no way to actually have a tree unless you can decide whether something comes before or after another element in your types. So if you wanted to store a person class in your tree, and you wanted to create a binary search tree, you would have to know whether or not one person came before another person in order to make that thing happen. Being able to draw binary search trees based on input and being able to evaluate whether or not something is a valid binary search tree is something that is an important thing to know. Okay, let's see. We have 4 minutes left, and I think in those 4 minutes, what I want to do is I just want to copy over our binary tree that we have right now, and I want to just get it ready to be able to become a binary search tree. And that's just going to entail coming to our code, taking our binary tree, copying it, and making one change to the data that we keep track of. Our binary search tree, in our node, this item right here, this bit of data, we said that it has to be able to be compared with itself in order to determine whether or not it goes to the left or the right. And that means that this generic type T can't be anything. It can only be something that's comparable. And so this is an example of where we need to qualify what T can be. And so what T can be is it can't be anything, but it has to be something that implements the comparable class. So we've restricted it. It's not as restrictive as if we said that our binary search tree is only going to work with strings or numbers. That would be a very specific class, and we wouldn't be doing generics at all. It's not completely open-ended where we can use any class. That was what we had before, just T. Now we're saying you can use binary search tree with any class you want as long as it's comparable to itself. And by making that change, we've now restricted the kinds of classes that we can use for T, because at some point we're going to have to make a call and say, T, we're going to have to take something of type T, like data, and we're going to have to say compare to another bit of data. And because we don't know what the type of data is, we don't know for sure whether compare to is present. But because we've now said T must implement comparable, now we know that we have a compare to method available to us. And now we know we can decide an ordering for the tree. So that's all we needed to do in order to make our tree able to be a binary search tree. Let's just go through. We've got our height. That's all fine. Our visitor is all fine. That's not going to change because it's a binary search tree. The only thing that's going to change is our set left and our set right. We're going to get rid of these because we're not going to allow people to set the left and right, because in order to maintain the contract of a binary search tree, they're going to just ask us to add something, and we'll do add child, and we'll put it where it belongs. But we won't do that today. Size and height remain the same. Visiting remains the same. All that's good. Add a child, and then we're going to have to implement the way that we add a child. All right, let's see. So basically what that means from today, the things that we did today and the things that we learned today and that you need to make sure you're able to do is that you need to be able to identify what a binary tree is and what makes a binary tree a binary tree. We need to be able to identify what a balanced binary tree is and to be able to determine the height and number of leaves that would be present in a balanced binary tree. You have to be able to and be comfortable with traversing trees of multiple depths in both pre, in, and post-order sequence. You need to get your head around the visitor pattern. And then finally, we started working on understanding the binary search trees. We're going to finish up a little bit more with binary search trees next class. And then I think the last thing that we're going to be able to tackle is red-black trees. And what a red-black tree is it is a way of implementing a binary search tree so that it stays bushy. And we like the bushy trees because they're more efficient. Okay? Any last questions online? Don't see anything in person? Okay, great. Thank you for your attention. A lot of work to do between now and Friday. We will see you tomorrow for our last lecture class, and then we'll be taking the exam either proctored or with proctor free. Thank you for your attention.